So good afternoon. First, I'd like to thank you for the opportunity to show our work. This paper has the co-author of Soren Bisgaard. And first, I will present our design, strip block design. Earlier, Sir David Cox was talking about randomization, and he mentioned that all models are consequences of the randomization. So I'll be showing some design strategies based on randomization. How can we choose a design? And we'll present a new arrangement that we are calling post-fractionated strip block design, and I'll show how we can conduct the appropriate analysis considering the randomization structure of this design. So the main topic of motivation for this topic is the industrial applications. So in industrial applications, a major concern is cost. So our research question is, how can we reduce the cost of experimentation? And we're considering two basic scenarios: the robust design applications, where we are interested in products that are insensitive to some different source of variation, and also multistage process. We are mostly conducting experiments in multistage process. We have an application in battery production, and also in Brazil, you are applying this design strategy in industry, in tile industry, they're producing ceramics. But today I will talk about the first application we used this strategy that was done in the United States in battery production. So we worked in Wisconsin, and in this city, Portage, that's the one facility of Rayovac that produce batteries. So we worked in this production line. So their problem at that time was high percentage of rejections on the battery production, and they have lots of dollars lost in this problem. So the customer requirements, they have two main variables: open circuit voltage and impedance. They had done a project before running an experiment to control the impedance. So now we're trying to control this variable, but you have to keep track of this one to still keep on in control. So here are some of the types of the batteries that they were producing, and we chose to work in this one here with this specific type. And this can be, the whole process can be separated in two main stages: the assembly process and the curing process. So this is the characteristic of the designs that we are going to apply. So we're using the applications in robust design and multi-stage process. What they have in common that's to use this technique is that the factors under experimentation can be separated in groups. In robust designs, we can separate in control factors and noise factors. In multi-stage process, we can, in this case, we separate the production process in two stages. Here, the assembly process, so we have some factors that will be associated with the assembly process, and other factors that will be associated with the curing process. So at that time, they had around 5% of rejections, and the cause of this rejection is high OCV. So the consequence of this high OCV is that the batteries are self-discharging. So when the customer goes to buy the battery, it's already completely dead, or will only last for a while. So it's pretty bad for the company to put those batteries in the market. So they had a 100% inspection of the outline not to ship these batteries to the customer. So they had lots of losing lots of money because of this problem. So our objective with the experiment is to identify the sets of some factors to reduce this percentage of defects. and also to reduce the variation. So some characteristics of the production process that we're going to incorporate in the design. So they have the production in 2 shifts. So we are going to run the experiment on actual production line. So have to run the experiment as quick as possible so that they could go back to their actual production. So they would like us to finish the experiment, if possible, in only 1 shift. So this is one of the restrictions of this application. And they also have only 1 Curie room. So all the batteries that are going to be run the experiment need to go to 1 specific room. And you have some factors that will be changed in that room. So we have 6 factors, 4 of them associated with the assembly process and 2 with the curing process. So now we're going to see some design approaches based on the randomization. The first approach would be a completely randomized design with 6 factors, each we're using 2 levels for each one. We'd have a total of 64 trials. And what would be the consequence? If you have a completely randomized design, you have to change the assembly configuration 64 times, and also to change the curing conditions 64 times. And each cycle of the curing stage will take at least 5 days. So if you're doing, remember that you have only 1 room. If you put only 1 experimental unit, it will take 5 days. So for using the 64, it would take 320 days. So it's impossible to wait that long for running an experiment. So a completely randomized design is out of question in this application. So this is a quick show of how would be the randomization pattern. We have all the 64 trials, and we would run 1 at a time. So the second approach would be to run a split plot design. So in this case, we could use the assembly variables as the whole plots. So we will reduce the number of changes in the assembly process. Instead of 64, we could use only 16 changes, and these changes could be run in 1 shift as they wanted us to finish in 1 shift. But on the other hand, we still need 64 changes in the current stage, and we still need 320 days to finish that. So it is also not a good approach here. So what would be the randomization pattern? First, we would produce randomly among these 16 changes of the assembly variables, 1 large batch of batteries that could be split in 4 small batches. And for these 4, we'd assign to each of the 4 conditions. So here, the row, each row is the whole plot. All of them come from the same batch of batteries, and each small batch is the subplot. So we have 16 whole plots, each with 4 subplots. And the other approach would be the strip plot design. So in the strip plot design, we would have only 16 changes for the assembly. So we could run all in 1 shift. And also we are going to use only the current configuration only 4 times. So we will reduce the amount to running the experiment, amount of time. So how is the randomization? We will get randomly 1 of the 16 combinations, run a large batch of batteries, split these into 4, and randomly assign each one to a specific current condition, and do this for all 16. So after we finish with all 16, then we randomly assign all of them. They will be simultaneously put in the current room. So all 16 sublots will be put together in the current room, and then we are going randomly the other ones. So you can save, we have 3 types of experimental units in this case. So you have the row, that's one type of experimental unit. All of these 4 sublots come from the same batch. And you have another experimental unit here, the column, because each one were put in the current room at the same time. And another experimental unit is each batch, each small batch. So if you have this is a strip block or strip plot design, and we have here all the 64 combinations. Now we are going to see what's our approach to reduce the cost of experimentation in this scenario. In this case, we have to include all 16 in the same current room. Let's assume that you cannot include all of them, but only half. Let's say only 8 of these sublots can be put simultaneously in the current room. So what can we do? One approach is to use a fractional factorial design. Instead of working with the 16 here, we can have a half fraction. So in this case, we would have in each current room 8 sublots. The consequence of this one, you get a resolution 4 design. It's the maximum resolution we can get working with a half fraction in the row design. But you have a different approach. Instead of taking a fraction factorial on the row design or on the column design, we are proposing to get a fraction on the combined design. That's why we are calling a post-fraction. After the combination of the 2 designs, we are going to select a fraction. So that's what we call a post-fractionated strip block design. So among all 64 runs, we are going to choose 32 runs. And you can notice that in each column we have only 8. So these 8 that will be put together in the assembly in the current room. So with this structure, we can go from a resolution 4 design to a resolution 6. So this design has resolution 6. So we are showing how can we choose these 32 runs. So before I'm going to that, I just say that you can reduce even more. If instead of 32, you can only run 16. So we can post-fractionate this and have less here. So we have only 4 sublots in each time we are using the current room. So in this case, we don't keep the strip plot structure. We reduce to a split plot, because if you see in each row, we only have 1 run. So it's no longer a strip block design, it's a split plot. So if the higher the order of the fractionation, we can reduce to a split plot design. So to preserve the strip block structure, have a maximum order of post-fractionation. So here we are calling F the order of post-fractionation. So K, it's the number of factors in the first design. first group, and Q is the number of factors in the second design. So Q minus P would be the order of fractionation, and Q minus R the fractionation of the second design. Since here we are not working with fraction factorials. In each design we are working with full factorials. We have 4 for K minus P and 2 for Q minus R. So our P and R are 0 since we are using a full factorial. If you're using a half fraction, you use 1 here and 1 here and so on. So the minimum here for this case is 2 minus 1, so we can only fractionate once to keep the strip block design. That's what I showed before. If we are going from 64 to 32, we keep the strip block design structure. If you fractionate once more, going to a 16, we lose the strip block, but keep a split plot structure. So how can we conduct this analysis? We can compute all main effects and interactions as if it were a completely randomized design. So it doesn't change the way you can compute the main effects and interactions. What we need to pay attention is that not all of the effects will have the same variance because of the randomization structure. So we need to identify each stratum, which effects will be associated with each stratum, that each stratum have a different variance. And we have to group these effects with the same variance, because we are in the scenario of unreplicated design. So we're going to do the analysis with normal probability plots, for example. And you can conduct separate analysis for each stratum. In this case, you have 4 different strata. For a traditional strip block design, we have 3 different types of errors and 3 different strata. But with the post-fractionate, we found another group. So we have 4 groups. So we have to separate all the effects in 4 groups. So how can we do this? The procedure, we first start with the post-fraction. So we'll get the generator of this post-fraction. This generator will be in one stratum. In this case, if we had only one generator, there will be only one effect in this stratum. If we had more generators, we include all the generators and all the interaction among all these generators. So the next step is to go for example, for one group. Here, the row group. So we have all the factors, A, B, C, and D, that they were associated with the row group, and all their interactions, except the interaction A, B, C, D, that is already here in the post-fraction. So we can do the same for the column group. We get all the factors associated with the column, in this case 2 factors, E and F, and their interaction, removing the ones that already appeared before. So since EF is already here, it's not here. And all the remaining effects go to the interaction stratum. So that's the procedure to identify which effects will go in each stratum. And each stratum has its own variance. And here is the expressions for each variance. So I'm calling variance for all the effects that are associated with the row, the effects associated with the column, the interaction, and the post-fraction. So these are the expressions for each variance. If we have replication, we can conduct an analysis of variance test with all these 4 groups. And if you don't have, like in this case, if you have no replication, we can conduct graphical analysis with like normal plots and length methods for each separate stratum. So it's important to identify which effects will go for each stratum to get its specific variance. For this example, we got some results for each one, for each factor, our recommendation. And this we analyzed the OCV and also other variables, like the impedance and other variables that were important for the production. And also we studied the within variability from each batch of batteries. So considering this is the recommendations only for the OCV variable. But with the considering all the other variables, we made other recommendations. So have these 6 recommendations for each level. And for our conclusion that we can use the post-fractionated design as a cost-effective method because we can reduce the cost of experimentation. We can incorporate the characteristics of the process to choose an appropriate randomization pattern to construct the design, and have to consider this structure to analyze the experiment. And to help the choice of generators for the post-fraction for each fractional factorial design for the whole design in the column design, we prepared some catalogs. So we use we have for 8 run, 16, and 32 run designs, and up to 11 factors. So we will have these catalogs. If you given the number of factors for the row design, the number of factors for the column design, and also the number of runs for the row design and the column design, considering all these numbers, we indicated what will be a good choice for generators for the post-fraction and each row fractional factorial and column fractional factorial. And we can show that the strip block designs, there are many applications in industry that can use this type of strategy. Because if you can see many applications, we have multi-stage process. And if you can split in 2 and can be extended, the same idea can be extended for a strip block design depending on the number of stages and factors that will be associated with each stage. We can generalize this approach. And it's logical. Like in this example, we've had only one current room. It's logical that we are going to use to put all the experiments, all the runs at the same time, that we are subject to the same settings. So we're not going to change every time. So this restricted randomization is very useful in industry. And also in the case of the assembly, if you have to change the settings of the machine, it's easier to change the set and keep that set and run several experiments and then change for a new set. So many experiments are run as a split plot or strip block design, even if the experimenter doesn't know. So it's useful to pay attention to this structure and incorporate this structure in the analysis. So just to show what was the result of this project, we had here, it's before the experiment, there was a high variability. So after the change, so we reduced like 80% of the defective rate and 75% on process variability. No? Thank you. So if you have time for questions.
There's obviously time for questions.
It seems to me, in your example, the interaction EF was in this stratum which you call the post-fraction stratum, which I think is the same as Qing Shui's supremum. If I was designing that, I would be very worried because that's a two-factor interaction and it's a stratum with a very large variance because you've had to combine two variances to do that. Weren't people worried about doing that?
Because in this case, they were more interested in these interactions here. Because in fact, they knew already what would be the effect of this EF.
So
there was not a concern in this regard.
So they were willing to make that.
Yes.
Yes, but
and here also, these two, because in this case, these two, we don't have a procedure to evaluate the significance of these two facts. But they are interested in this here, mainly interested in this one, and in this kind of interaction.
Okay, thank you.
So to run the design this way, they'd make a batch of batteries and then cure some and wait, and then cure others later. And so there's no, you could ignore or neglect any time delays between production and curing.
No, they would like to have that, but in fact they couldn't change the time for the curing process.
I mean, as I understand it, you had 16 different combinations for A to D.
Yes.
And a combination of, let's call it a lot, so you had 16 lots of batteries that were produced. And some of that 16 would be cured at one period and others would be cured at a later period.
Oh, in fact, in this case, the two factors that were considered, we could split from these two factors, you can generate like 4 combinations. So we could split the curing room in in 4 groups, and they could be independently
Cured at the same time.
at the same time.
I suppose, statistics aside, from an engineering point of view, the natural question is whether you could identify causally what created such a huge improvement.
Yes.
Were you able to tell them? I mean, I'm curious myself.
Yes, it's
Because I've had batteries that sit on the shelf and die, and I kind of wonder.
yes, I told them, but I cannot tell you. So that's why I didn't. I am just calling A, B, C, D, and F, so I'm not allowed to tell which one are them.
Understood.
It's a very important information.
Okay. Well, let's thank the 3 speakers of this session on multistratum experiments again, and then go for some tea.